Вы сейчас...
А ты можешь закрыться. Я могу закрыться тут, но тут вообще нечего делать. А в Питере хотя бы что-то.
Ладно,
Да.
сделайте оценку.
Вы еще у сестры зачетного кружка. 27-го.
Зачетных кружков?
Ну,
под зачеты есть даже.
на кружке. Ну, то есть
Вы
ладно,
отдадите?
да. Нет, она учится не в Питере. Да. Она, была еще теория рассказывает, таблички всякие, комбинаторики.
Что за логика?
Математические.
Скажите что-нибудь.
Говорю что-нибудь. Слышно?
И поэтому зачет, но она вот и есть.
Да?
Да.
Отлично. Ага.
В общем, мы изучили один предмет. Определение и деление состава.
Либо лучше нам доказывать просто. Главное, все сделать, потом вовремя сослаться на теорему.
Окей. Лемма.
Случайные величины.
Лемма ложь, это будет сложно. Ты ее помнишь?
Конечно. Ну, буду помнить.
Причем тут два варианта. Один, который формулируется, а другой формулируется.
Ну там легко, типа, там нужно просто d на d плюс d минус 1 на d. Так, типа, такие проблемы. Случайные величины их распределением от ожидания понятно. А ты вообще лекции слышал, да?
Я читал. Это и еще хуже.
Хорошо,
Ну, ты же сам говоришь, там доску на лекции не видно.
ну как, там видно в определенных местах, знаешь, типа вот, есть места как бы черные пятна, есть белые пятна. Белые пятна видно, черные не видно. Это какое как директор установить, что не видно на черных пятнах.
Может, это полезно. Так, ладно. Хорошо, это все ясно.
Он еще любит типа другие нотации делать. Вот одни нотации, а там доски другие, причем еще бывает так, что они заменяют доски нотация А здесь, значит, совсем другой на доске. То начинает включать здесь типа на доске.
So let's start. The last time I was moving very slowly, so we were caught in the middle of proving this principal ideal theorem. So we had an algebraic variety, x irreducible algebraic variety, and f was a regular function, and then each component of the zero set has dimension exactly dimension of x minus 1. Okay, so that's what we're in the middle of proving, and what we did prove last time. Pardon me? Yeah, irreducible. Yeah, each reducible component. So we proved the key lemma that if x is an irreducible affine variety, and f again is a regular function, and we assume that the zero set has dimension less than dimension x minus 1, then this function is invertible. Okay, so we proved this, and now let's go on with the proof of our theorem, assuming this lemma. So let's prove another lemma. Say this was lemma 1, and let's prove lemma 2. That if we have again x an irreducible algebraic variety, and u in x open subset, open subvariety, then dimension of u equals dimension of x. Okay, and simultaneously, hopefully, this will solve whatever difficulties you had with home assignment, or you're going to have, and then with the next home assignment. Okay, so let's first consider the case when x is the affine space, and or maybe first let me say that clearly the dimension of u is at most dimension of x, because if we have some chain in u, we can take its closure and obtain a chain in x. Okay, so this is clear. Yeah, and now let's take x the affine space. Then we know that the dimension of u is at most n. On the other hand, we can take the standard chain, the same as for the whole affine space. Yeah, so let's take a point in u, say point or u, small u, and then let's continue u, the small u, in a line L intersected with u, and then plane intersected with u, and so on. And this will be a length n chain. Okay. So it works for the affine space.
Why do the different sets?
Because this is open. For example, why these two are different? Yeah, because this one is open and non-empty in the line, and this is open and non-empty in the plane. So they clearly cannot coincide.
Because they
are non-empty.
Very different.
For a variety of reasons, but the main point is that they are non-empty because they all contain this point, small u. Okay, so now x affine and irreducible, and then we can by M-Noether lemma we can consider a finite morphism to some affine space, finite surjective. Okay, so we have.
Можно вопрос?
Yes.
Surjective обозначает, что на уровне колец субъективно? Или...
No. At the level of points. At the level of rings, it means that k of x contains this polynomial ring, and this is a finite module. Finite type module. Okay? So it is a subring such that the ring of functions on X is a finite type module over this. Okay? And any questions?
Yes, I want to ask, can you repeat why they don't
Coincide.
Почему вот эти вещи могут не совпадать?
Because this intersection is open in the line. So it cannot coincide with the point. On the other hand, this intersection is open in the plane, so it cannot coincide with anything open in the line. Okay, so we have this finite surjective morphism by M.Finkelberg lemma, and let's consider the complement. Say z is x minus u, and this is it's a union of a few irreducible components, but they are all strictly smaller than x. And last time we had a lemma which said that the image of this z in an must be strictly smaller than the image of x. Pi of z is strictly smaller than the whole an. So we can consider the complement, and it's closed. And we set, say, v in an is the complement. An without z. So it's open, and we can consider u prime, that is the whole preimage of v. So this is an open in x, and we have the containments u prime is in u in x, and this projects onto v inside an. Okay, so because of this, we know that the dimension of u prime is at most dimension of u, and it is at most dimension of x. And on the other hand, the dimension of u prime is the same as dimension of v, right? Because there's also this pi is also finite surjective.
So вы там имеете в виду P/Z, да? Когда
Pardon me?
right?
Here, pi of z, right? Right, thank you. Okay, so again, another claim from the last time was that the dimensions of are the same if we have a finite surjective morphism. Okay, so these two dimensions are the same, and this is the same as dimension of an. This is n, and this is the same as dimension of x. Right, because again, this is a finite surjective morphism. So hence, the dimension of u prime is the same as dimension of x, and hence dimension of u is also the same. Okay, so we have proved this second lemma. Maybe I'll erase it. Now we're ready to finish the proof of the theorem. Yes.
Может быть такое, вот если у нас не алгебраическое многообразие, а просто какое-то, и мы возьмем наше определение размерности. Может случиться так, что там какое-то подмножество будет иметь размерность больше, чем само x.
Bigger than x.
С такой ужасной топологией.
This I doubt. This I doubt. No, I don't think so. Okay. So now we're proving the theorem. And we have a component Z of our zero level set. Okay, and let's find an open affine U and X, which contains, which intersects with this component non-trivially. U intersect with Z is not empty, and then take a function, say h, on U, vanishing on all the other components of the zero set. Okay, but not vanishing on this component of interest, on Z itself. And this way we will somehow restrict our attention just to this particular component Z and get rid of everything else. So we take the function h that vanishes everywhere else, but is not zero on Z itself. Okay, and then shrink U to dH. Okay, so we remove the zero set of, remove the zero set of H. So in particular we remove all the other components, but this Z component remains.
This function is not regular, just a set function.
Pardon me?
H is a
regular function on U.
And why such this?
By definition of closed. Anything closed is the zero set of some function. And if all the functions vanishing on the other components would vanish on Z as well, then Z would be the closure of everything else. But it's not, by definition, because it's another component.
For each component we take a function and then multiply.
For example, So, how to say it? For any closed subset, say Y inside the spectrum of any algebra, and a point, say X, that lies in the spectrum of algebra but does not lie in this closed subvariety, there is a function h A such that h on y is 0, but h of x is not 0. That's just by definition. Do you agree? Because once again, the fact that y is closed means that there is a function which vanishes on y.
Exactly on y.
Yes, and if any such function would vanish on this point x, it would mean just by definition of topology, the Zariski topology, that x is in the closure of y. But it's not, because y is closed and x is not in y. Okay, so this is for free. Okay, so we replaced our u by u prime, and now the zero set of our function f, restricted to u prime equals 0, is exactly z intersected u prime. Okay, just one component. Fine, and now we have this this lemma. So the dimension of dimension of u is dimension of u prime. Say this is dimension of x, and then by this lemma, each reducible component of the zero set must have dimension x minus 1, otherwise the function would be invertible, but it's not invertible because it does have some zeros. Z intersected u prime. We also know by the previous lemma that this is the same as dimension of z, and this must be dimension of x minus 1. Okay, so the theorem is proved. Okay. Now there is the standard, simplest sort of counterexample to the converse statement. I mean, it's true for the affine space, right? So recall last time that any closed subvariety z in the affine space, if it has dimension n minus 1, then z is the zero set of some function, of some polynomial. Okay, but for arbitrary varieties it is not true, and probably everybody knows the simplest counterexample. So for x, let's take this cone, quadratic cone, xy minus z squared equals 0 inside the three-dimensional affine space. Right? And let's take just one line here. This is L. L inside X. It's certainly one. So dimension of X is 2. The dimension of this line is 1. What is the equation of this line, or an equation, or whatever? How is this line cut out of the quadratic cone? Well, any suggestions? Pardon me? Say y equals 0, yes, but it's not. That the point of this counterexample is that it's not enough. Yeah, so z is also equal to 0. Yeah, but somehow it, how to say it? The let me say it intelligently. The ideal in k of x of functions vanishing on L is not principal. So it has these two generators, but it cannot be generated by a single equation. Yeah. For example, if you impose just y equals 0, it will follow that z squared is 0. But here you need z itself equals 0. Okay.
Мы не можем касательную плоскость?
So what's the question once again?
Может здесь касательная плоскость, которая вот так вот будет касаться?
Yes, certainly we can. And so what?
Ну, будет уравнение.
But because it's tangent plane, it will intersect the cone somehow with multiplicity 2, so to say. So it'll be this double line. But the line itself is not given by a principal ideal. Okay. Later on we'll discuss divisors. Yeah, the divisors are certain combinations of codimension 1 varieties, and we will see again that this is the simplest example of a Weil divisor, which is not a Cartier divisor. Okay, so what else? We'll need two more facts, just an easy corollary of what we had. Assume we have a chain of closed subvarieties, Z0, inside Z1, inside Z2, and so on, Zn, and they are all distinct and irreducible. X is an algebraic variety, and now if this chain cannot pardon me. Pardon me? Yeah, well, doesn't matter, I don't know.
Просто если все равно ZN, напишем, что они ZN это слово замкнутые.
Yeah, irreducible, yeah.
Получается, что X тоже irreducible.
Yes, that doesn't matter, yeah, you'll see. So if the chain cannot be made somehow more dense, cannot be refined, I mean, you cannot squeeze anything else in between. So there exists no Z whatever I plus 1/2 in between Z I plus 1 and Z I. Then the dimension of Z I is exactly I. Okay, and I mean, for the J is J, for any J. and here for any I, yeah. If you cannot put anything else in between, then the dimension is just 0, 1, 2, 3, and so on, up to n.
There is no another chain which would have more close vertices.
You say that it's not absolutely evident, or what are you saying?
It's not obvious.
Not obvious, yeah. There is something to prove, yeah. Well, it's just by induction on n, so to say, or on j, and we start from certainly from a point, because if otherwise it would take a point inside, right? So clearly z0 is a point, so its dimension is 0, and now induction in j. So just let's prove it by reduction to absurd. So assume that a dimension of z j plus 1 is at least the dimension of z j plus 2. Yeah. And then by lemma 2, today's lemma 2, we can replace everything by intersection with some open affine U. Okay, and then for this open affine U, we can take a function f on z j plus 1 intersected with u. So there's an affine variety, so there's a lot of functions such that f restricted to zj is 0. Okay, but the function is not 0. And then we know the dimension of the zero set of this function is the dimension of j plus 1 minus 1. And so this is strictly bigger than the dimension of zj, and has this zero level set is strictly bigger than zj. Okay, so just take any component of this zero level set, and there we are. For z j plus 1/2. Okay, so we can start this refinement.
And we get such a function with these.
Is this just because u is affine, this intersection is closed, so it's also affine, and we discussed. Oh, here it exists just by this.
They all are closed, okay?
Yeah. Okay. And the last fact of the sort is fact 1. Fact 2 is that assume X is equidimensional. Equidimensional. This means that all the irreducible components have the same dimension. And y in X closed and also equidimensional. But of smaller dimension. Okay, so X may have some irreducible components, like this, and Y inside can also have some irreducible components, yeah, like this or that. So Y is dotted, X is the ambient thing, and then there are regular functions. Maybe again, to have functions, we need X to be affine variety. There are functions f1 and so on, fn in the ring of regular functions on X, such that all the components of the zero level have dimension the same as y here, and all the components of y are inside. Okay, so y lies here, but perhaps there are some extra components. Okay, so we can cut out our y by this system of functions, but perhaps there will be some extra components, but all of the same dimension. Okay. So the proof goes by induction. Yes?
We can cut out just y because it's closed.
No. No, not necessarily. So induction in the dimension difference. X is affine, yes. And y is also a fortiori affine. Pardon me?
F1, F2, and so F5 is the regular sequence. Meaning that the next one is not a zero divisor.
You can try to do this, but I don't see. So what do you claim?
Otherwise, y is closed, so we can just cut out y by equation.
Yes.
So, sorry, I'm still blank on what you are saying. Are you proving this or disproving, or what are you doing?
But someone said that it's trivial because...
This is trivial.
Yes, because y is closed, so it's a zero set or some function.
Yes, but the point is that all the other components of the zero set are of the same dimension.
But there are no other components.
How do you mean? There are. No, I don't claim that. So to say, y is a complete intersection. It's not true. You can cut it out, but you will get some extra junk.
Еще быть объединение, поэтому у нас возникает проблема.
Замкнутое
Объединять.
это не обязательное решение системы.
Да.
Then we should require that the number of this function is equal to the difference of them.
No,
Чтобы умножать функции.
no, I don't see why. I don't see your point somehow. You will, I know, you may get some extra thing like some extra component here. I don't have a color chalk, seemingly, or maybe I do. Yeah, so you may get something extra like this, but then if you try to remove it, you will have to pay a price by losing some components of y. In principle.
Нет,
It's
вообще,
possible.
правда, можно просто взять идеал y, взять его порождающий, тогда
And so what?
ровно y вырежем. Надо что-то от n потребовать. Нет?
Что такое по определению замкнутое множество? Это не то, которое задается вот такой вот системой уравнений.
То есть получается, что если мы рассмотрим такое множество, где f1 и f равно нулю, это будут ровно точки y и больше никакие. Можно взять такие
Они будут в иксе замкнуты.
No.
замкнутая система, в x расположена.
Okay, maybe let's say that n is the dimension of x minus dimension of y. Okay.
So it's about
Maybe this makes sense. Okay, so in induction, in this, and what do we want? We want to take a function, say f1, that vanishes certainly on the whole of y, but does not vanish somehow anywhere else. So f1 of xi is not 0 for some points xy, say 1 in each irreducible component of x. Okay, so then we replace x by the zero set of f1. Okay, and in each irreducible component of x, you will this function does not vanish identically, so you will lose exactly one dimension. On the other hand, y will remain intact, so we will be in a good position, okay, to continue. And now you have to find such a function, and such a function. Well, we almost had it here before I erased.
Мы сказали, что вот если мы возьмем, значит, афинное многообразие, в нем возьмем какую-то функцию f, то и размерность нулей это dmx минус 1.
Yes.
Обратно, если у нас есть многообразие размерности 1, то обязательно ли оно сдается?
No, we just had this counterexample. No.
Вот да.
Yeah.
А тогда взяли сейчас одну функцию, мы ждали одну функцию и сказали, что
Это получится не все.
Да. В этом проблема.
Yes. So let's do this. So we fixed some points on in each connected in each irreducible component of x, and now we have these points x1 and so on, x capital N.
Можно вопрос?
Yes.
Мы тут хотим взять такую функцию, которая разумляется на y, и разумляется хотя бы на одной точке каждый другой компонент.
Yes.
На каждой компоненте x.
Yes.
То есть y занимает целую компоненту x.
No, it cannot, because x is equidimensional. All the components are of some big dimension. Y is also equidimensional, smaller dimension, right? And so it cannot cover any whole component of x. Okay, so these are, so to say, representatives of irreducible components of x. Okay, 1 point for each component. Now let's construct whatever functions h1 and so on hn. So hi vanishes on the whole of y, and also these points x1 and so on, but not xi and x capital N. So this is a closed subset, right? So you can find such a function as we discussed before, but hi of xi is not 0, say is 1. We can't do this because xi does not lie in the closure of everything else. Okay, and now finally our function f1 will be just the sum of those hi. Okay, it has this property evidently. So that's it for dimensions. And now let's move to the topic of Cartesian products, direct products. So, in a sense, another new way to construct new varieties. Okay, so we have two varieties x and y, and we want to construct their product, and the obvious problem, as in the very first home assignment, is that it's unclear how to equip it with a topology. So this has some topology, this has some topology, and their product certainly we don't want to equip it with the product topology. we want some new topology. And we will do this in 2 steps. So for first, we don't even consider algebraic varieties, we just consider arbitrary ringed spaces, okay, ringed with some regular functions. And then I claim that there exists unique space, say Z. This will be their product. It's another ringed space. With the following universal property. Maybe universality. So first of all, this Z must project both to X and to Y. And now, given some other test variety, for a test ringed space, S, we have that the morphisms from S to Z certainly map to morphisms from S to X and to morphisms from S to Y. Right? Just by composition with those 2 projections. And we require that this is an isomorphism. Okay, just by here composition with per X and per Y.
It means it's just a bijective map of sets or something.
Oh yes, yes. We don't have any structure on morphisms. It's just a set. Okay. So yes.
What about step production here? We said that if we take Y,
Y, yes, yes, yes,
y
yes.
dimension equal to dimension of X minus Y, we take one function F1 is equal to the sum of HI. And
yes.
Then
and then we replace X by the 0 set of this function. And then by our principal ideal theorem, it will be again equidimensional. Because yeah.
We should do the same again.
Yes, 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 yes. But nobody tells you that in the end you will obtain just Y. You will obtain Y and a few extra components of the same dimension. Okay. So in other words, in a scientific language of categories, let's say the category of ring spaces S equipped with morphisms S to X and S to Y has the final object Z. Okay? And just for fun, I wonder if anybody, if everybody heard these words before, but maybe you know how to construct this Z also.
I have heard this word, but I even don't understand why this definition is same with writing below word.
But well, if
final object is when we have a morphism to it from any.
Yes. We didn't construct it yet, but somehow this claim just exactly means that, right? Because every S equipped with two morphisms to X and Y automatically acquires a morphism to Z. So this Z is just by definition the final object of this category.
So we have a morphism from anything to Z.
To Z, yes. Z is the final object. Huh?
Okay.
Okay. Fine. So construction. Yeah, but by the way, since everybody heard these words, then you know that this is the key point isn't this article, right? The final object is uniquely defined. It may not exist, but if it exists, then it's uniquely defined. Okay, so we only need to construct it. As a set, X is, Z is the product, just like this, but we need some finer topology.
Excuse me.
Yes?
In our category, when we consider a morphism, should it commute with morphisms to X?
Should it commute?
You define category.
Oh yes, certainly, yes, certainly, yes.
Okay.
S1 to S2, and they are equipped with morphisms like this, yes, and everything should commute, yes. So we need to find the topology then, the product topology, and somehow it's just imposed on us by this requirement. So this topology will be sort of Zariski with respect to supply of regular functions. And the regular functions are just the products of regular functions on X and Y. But if it would, yes.
Regular functions is a sheaf defined on open.
Yeah, I will, yeah.
But there is no open things now.
They will somehow appear automatically. But even globally, what do we expect of the functions? Certainly we expect the exterior product of functions, yes? So if we have, say, f a function on X and h a function on Y.
There can be no functions globally.
Yes, I understand. Yeah, we will cover everything, momentarily. But well, say assume that they are affine or whatever. So if I have two functions, we do want their product. But if we only had such decomposable function of the product, we would have just the product of two topologies on X and Y. That's what we don't want. But certainly you have also the sums of functions like this. So you also need the sum of fi hi. So any sum also must be there, just because you can add functions. And that's already enough. So for any... Yes, but I will give a strict definition right away. For any collection of f1 and so on, fn, functions on x, and h1 and so on, hn, functions on y. So this is the definition. The only problem, as everybody tells me, is that it's too global. So now just make it locally. Okay, so take an open u in x, v in y. Now take those functions f1 and so on, fn on this open in x, h1 and so on, capital N, the functions on v, and now take function the sum of fi hi on the product u times v, and it so certainly it can vanish somewhere, right? So just remove its zero set, so it vanishes on some, say, I'm running out of letters, maybe w in u times v, and somehow the basic open set. Maybe I want a name for this function, say g. Okay, dg is u times v without w, and this is in u times v. Okay, and so these guys will form the base of topology. Okay, such dg form a base
So there will be more
of topology.
open fields.
Yeah, certainly you can take their unions and maybe intersections. Yeah, you know how to produce.
I need more of them in our product topology.
Oh yes, certainly, yes, clearly, yeah, because I know you solved the first home assignment, so you.
Totally about that.
Yeah. Okay, and the sheaf of functions somehow is, well, so say glued from functions of the sort g prime over g on dg. Okay. So g is a nice function, but it does not vanish on dg. So we must be allowed to invert it, and we do this. We're allowed to invert it. Okay, and then this will work.
What is g prime?
Any other function of the same type.
As g.
Yeah. So G prime is the sum of f I h, maybe f prime h prime for I goes from 1 to capital M. And again, it's restricted to this basic open set. Okay, and then you just routinely check that it does form a sheaf and all the properties of ring space we postulated at the very first class, and then you check this property, and there you are. Okay, and now one evident thing is that if U in X and V in Y are open, then the product is also open, and similarly for closed, the product of closed subspaces is closed in the product. This is all clear. So Z in X and W in Y closed. Hence Z times W in X times Y closed. Okay, and now coming back to our algebraic varieties, we prove that if X and Y are algebraic varieties, then X times Y is an algebraic variety. And moreover, if they are affine, then their product is also affine, and it is the spectrum of what? I guess everybody knows. Yeah, tensor product. So maybe everybody knows this, or shall I go over it?
Yes.
Yeah. Okay. So first of all, if we know this particular case with a concrete calculation, then we know A just by open covering. Because every variety is covered by finitely many affine open subvarieties. For affine we know B, and then the products are also open, and they cover the global product. So this will give us the required cover by affine open subvarieties. So we have to check B, and to this end we first check that this tensor product is an algebra we like. I mean, it's finitely generated and without nilpotence. Okay, but it's finally generated evidently because just if you have generators of A and B, their products will be generators. Say A1 and so on, AN, and here B1 and so on, BL, then AI, BJ, generators of tensor product. This is clear. What about nilpotents? Any suggestions about nilpotents?
Элементы в АБ, это А, запятая, Б, в скобочках, и мы должны это перемножать.
Нет, это плюсика B плюс плюсика D.
Все равно
Вот, и теперь перемножать. Понятно, что разложение...
Yeah. So as far as I know, there's no immediate proof for this, and we have to go back to spectra. So it's a sort of dirty trick proof. So if we know that this tensor product embeds into the functions on x times y, x is spectrum of A, y is spectrum of B, then certainly the ring of functions does not have any nilpotents.
Then it's too dirty trick because they are using statements that we are proven.
No, there's just a set, nothing else, just a set. Since the ring of functions has no nilpotents. Okay, so we only have to prove that there is such an injection, right? So we have to check that if well, maybe F1 and so on, Fn in A are linearly independent, and say G1 and GL, sorry, well, those N and L are different, or also are linearly dependent, then in fact they're slightly different because they are yes.
А почему концовка X на Y не имеет нилпотента?
Just because this is the ring of functions of certain particular, regular, I don't care, but at least they are just functions on this set. Yes? And the functions cannot have nilpotents. If some function, just because they are multiplied pointwise, if some function is 0 to the 5th degree, then it's 0 totally everywhere.
But maybe there is even no such functions because we don't know it's a hidden yet.
Yeah. Okay. So G whatever M also linearly independent. Then the sum of F I G I
defines a non-zero function.
Yeah.
Excuse me, we know that such map exists and we are proving that it's injection, or we don't know even that this map...
Right. The existence, that's a good idea, yeah. The existence is as follows. Phi of... phi of the sum of f I tensor gi from y to m is just the sum of f I gi.
And
Yeah.
know that it's a regular.
We just well, maybe let me put it of x times gi of y. Oh, yeah. So it's clear what I mean, I hope.
We know that it's a regular function.
No, it doesn't matter. Once again, I'm not using anything here. I only say that I know that A is functions on x and B is functions on y. This I do know. Then I consider just the product of two sets.
And take
And I, given a tensor element like this, I assign to it this function on the product of sets. It's just a function on the product of sets. I don't care about anything else.
This k and square for brackets is in that category. And not a regular function.
Okay. Functions on x times y. Okay? And now I claim that if this is not 0, then this is not 0. So if it's not 0, then no, maybe, pardon me?
Там выбрали просто линию независимого семейства, да?
Ну, мы выбрали не нулевой элемент тензора.
But maybe the non-zero element is made up not like this. I'm sorry. Maybe it's m and still here it's l. And now I take the sum over I and less than or equal to m and j less than or equal to l, something like this, yeah. And fi g j, and this must be not 0. I think this is the definition.
Any non-zero element of tensor product has such form. Without alpha ij.
I mean, the relations in the tensor product are such that if those are linearly dependent and those are linearly independent, then their tensor product are also linearly independent. The collection fi tensor gj is linearly independent. And we have to prove that their image is their images are also linearly dependent.
Did you say that
Fi of x gj of y is also linearly independent? Yes.
Did you say that any element of tensor product has such form like sum of fi j? I think it's not.
But by the very definition, any element of tensor product has the form like this.
Yes.
But we have to check that there are no relations between such elements.
Yes.
Namely, in the tensor product, we know that if separately f's are linearly independent and g's are linearly independent, then all such guys are linearly independent. Right? I1 runs from y to yes. And j runs from 1 to l.
Yes. My question is about writing on the board.
So
What expression will okay?
things. So we have to prove that these are linearly independent. Let's prove this. Suppose there is a linear dependence. Cij fi of x gj of y is identically 0. Then it is 0 for any point of x. So it's on x and y. Hence, maybe let's call it h. Okay, but then for this particular fiber, this will give us a relation between the functions g, j, right? And this means that the sum of C I j over I, yeah, fi of x will be identically 0 for any j. But this is a relation between functions f, and they're linearly dependent. So all of those c's must vanish. On fi's. Okay. Okay. So we proved this, and we know that this tensor product algebra is good, and it makes to take its spectrum. Okay. On the other hand, we know that in the category of algebras, the tensor product of two algebras does play a universal role. Okay, so if there is some third algebra, C, and we have a morphism from A and also from B, then necessarily there is a morphism from, and a unique morphism from A tensor B to C. Okay, and this I hope everybody does know. At least I have no time and no vitality to explain this. And finally, we know that the category of algebras is anti-equivalent to the category of algebraic varieties. I mean, I have affine algebraic varieties. But with opposite arrows. Okay, so since we know that this guy solves this universal problem in the category of algebras, then its spectrum will solve the universal problem in algebraic varieties.
And this will be problem with reversed arrows.
Yes. Yes. So there we are.
And algebras over K.
Yeah, the algebras over K, finite generated without nilpotence, unital, and the standard mantra. Yeah. Okay, so that's it for today. Thanks. And sorry again, I am too slow, but Hopefully before retirement we'll reach something
А вообще
eventually.
категории
Yes.
кольцованных пространств, там пределы они есть все? Категория кольцованных пространств есть пределы?
Нет, в смысле, такие абстрактные